Hello, Integrating Man here. Today I have an interesting integral that has a lot of applications. We're going to figure out the following infinite integral called the nth moment of the Gaussian, or maybe 2nth moment of the Gaussian. The integral from minus infinity to infinity, x to 2n, we're in some integer, e to the minus alpha x squared dx. Alpha is a positive real constant. Our integral will rely on our knowledge of the usual Gaussian integral. That was derived in video number 1. I'll put the link in the description. All right, so there's a trick to being able to do this. I'll show you the trick. Let's consider the integral from minus infinity to infinity d alpha e to the minus alpha x squared dx. Notice that if I take a derivative with respect to alpha, the x squared is a constant with respect to that derivative, and so I would bring it down. So this would be minus the integral minus infinity to infinity x squared e to the minus alpha x squared dx. Okay, if I repeated that, say with two derivatives with respect to alpha, and since there's a minus sign that gets picked up, let's put a minus 1 squared. This case isn't going to be that, that's not going to be anything, but we'll write that in there anyways. If I take the first derivative, I will end up with minus 1, because I'll bring down a minus sign from here, and that will cancel one of the minus signs here. d alpha x squared e to the minus alpha x squared dx. This derivative with respect to alpha goes right past the x squared here, since that's a constant with respect to alpha. And I will end up with the integral minus infinity to infinity x to the 4th e to the minus alpha x squared, where the minus sign, minus x squared that gets brought down, one of the minus signs cancels with this. Okay, now what's pretty interesting about this is this integral here, this derivative with respect to alpha. The integral's over x, and the limits of the integral don't depend on alpha, and the integral is convergent. That means I can bring those derivatives right outside the integral here. So I could write this, for instance, as minus 1 squared d alpha squared, integral minus infinity to infinity e to the minus alpha x squared dx. Well, this is the usual Gaussian integral, simply equal to square root of pi over alpha. So, I'm taking moments of the Gaussian, the integral minus x to infinity to infinity x to the 4th e to the minus alpha x squared will be minus 1 squared d alpha squared square root of pi over alpha. I'll write alpha to the minus 1/2. All right, well, in that case, it's just going to be minus 1 squared minus 1/2 from one derivative minus 3/2 from the next derivative, alpha to the minus 5/2 root pi. One of these cancels with this, another one cancels with this negative sign here. And you end up with square root of pi alpha to the 5th. And then I get a 1 times 3 over 2 squared. Let's do the general formula. It's basically repeating the same thing. The general formula, as hopefully you can see, is the integral from minus infinity to infinity, x to the 2n e to the minus alpha x squared dx. Every x squared could be replaced by a negative dd alpha. And every one of those negative dd alphas could be brought outside of this integral. So I would get negative 1 to the n d alpha to the n of those, integral minus infinity to infinity e to the minus alpha x squared dx. This integral is root pi over alpha. So this is equal to minus 1 to the n d alpha to the n square root of pi over alpha. This negative 1 should be inside that brackets. All right, so I could take those derivatives with respect to alpha. I get minus 1 to the n from here. I get a root pi, since that's a constant. I will get minus 1 half, minus 3 halves, minus 5 halves, etc. n times. So there'll be n, I'll get all the way up to the nth odd number. Well, that's negative 2n minus 1. I can see this because the first odd number, so if n was 1, is 1. So I would expect, so 2 times 1 minus 1 is going to be the first odd number, which is 1. 2. And then there's going to be a alpha to the 2n plus 1 over 2 here. All right, let's clean that up a little bit. So we will end up with the integral from minus infinity to infinity, x to the 2n e to the minus alpha x squared dx is going to be equal to, notice here, there are going to be n minus signs from bringing it down. And there should be dot, dot, dot here's on those derivative things. And those will all cancel with these n minus signs. So all the minus signs cancel. I'll have 2 to the n power in the denominator. And then I'll have all the odd numbers up to this 2n minus 1 in the numerator. So this is going to be equal to square root of pi over alpha to the 2n plus 1 1 over 2 to the n. And then the way that we can write all the odd numbers multiplied together is to write this as 2n minus 1 double factorial, where the double factorial notation is either all the odds multiplied together up to this point or all the even numbers multiplied together up to that point if I had, say, 2n double factorial. Well, this is the formula for all the even moments of the Gaussian. All the odd moments are 0 because you're integrating a odd function then over an even range. And that's all I have for you today. If you like this video, please hit the like or subscribe button. Have a good day.